So hashing is actually a process inside ADT dictionary, meaning dictionary ADT lah, data, abstract data type of dictionary. So in order for dictionary, for this ADT to work, it needs hashing process. So we will learn about the hashing method. So in this chapter, we will learn about write application program that use this dictionary, this ADT dictionary. Okay, so in order to use this dictionary, we will need to override a method called hash code. Okay, so we will learn later where is this hash code coming from, meaning from which interface. And then after that, you both will learn about how to implement hash functions and collision resolution schemes. So when you are doing hashing, there will be a problem called collisions. So in order to solve that problem, so we will learn about three types of collisions resolution schemes. So um, that three resolutions can solve collisions. So after that, we will learn about the advantages and disadvantages of various hashing and collision resolution schemes. And then after that, describe clustering and the problem it poses. Okay, so maybe in this session, we will cover up until three this subtopic. Okay, so the, when we want to compute a frequency of words, okay, so maybe you have one text, one file that has a lot of text, and then you want to compute the frequency of words, any words, each of the words inside that text, how many it is cited lah. Okay, so how many time it is written. Okay, so what ADT that you want to choose in order to compute the frequency of words? First, maybe you can choose either list or ordered list. So what type of implementation? Either you want it to be in array or link. And if you are using ordered list, either you want to use the implementation of array or link or binary search tree. Okay, so all of that we have already learned previously. So, or lastly, we can use actually dictionary in order to compute frequency of words. So, this is the interface class that has the hash code method. Okay, so the object class is the interface class that has the hash code method. So whichever class that implement object class, they need to override the hash code. They need to override the hash code and produce their own suitable hash code. Okay, so a hash code should depend on entire search key. Okay, so we will learn what is key later. Okay, so um, another point to consider when you want to compute the frequency of words is what type of algorithm, hash code algorithm that you want to use. Okay, so let's say we want to store words meaning a lots of word lah, and then update their count or frequency based on the words itself. Like I said just now lah, if you, for example, if you have one text file, uh, for example, test.txt lah, and then in that txt you have a lot of words in there, and then you want to calculate the frequency of each of the words inside that text file. Okay, so There are more than one algorithm that you can use in order to calculate the frequency of the words. Okay, so for example, you want to use a method which is to sum up each character integer value. So meaning to say that if you have a text file, uh, let's say you have this text file. So this text file have this. So we want to check each this word how many times, this word how many times, and this word. So we can see here test is there are 3 tests. So the frequency of test is 3. So the method, if we want to calculate the frequency of word, maybe we can have this method lah. You can have another method, but maybe this is one of the method, which is to sum up each character integer value. Each character meaning this character, this character, this character. It is not each words, each character integer value. Meaning you want to sum up the character value, the integer value of T, E, S, T. So you want to sum up this lah using its integer value. So option for in character value, maybe because here it says that you want to sum up that integer value, right? So that integer value is coming from where? If you see here, this is only a word or a alphabet, a character. There are no any integer here. So where do you get that integer so that you can sum up? Okay, so there are 2 methods to get that integer. For example, you assign integer 1 until 26 because our alphabet, there are 26 alphabet, right? From A until Z. So A, capital letter A, start from 1, and then capital B, capital letter B is 2, capital letter C is 3, up until 26. So all of the capital letter A until Z is represented by 1 until 26. And then for the small letter, it is represented by 27 until 52, meaning the continuous of 26 lah. Okay, so small letter A will be 27, and then small letter Z will be 52. Okay, so that is maybe one of the method that you can get in order to get the integer value of a character here. So maybe T, I am not sure. T, you calculate A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T. It is element 20. So T is 20. T is 20. E, you calculate yourself. Okay. So test, we will have the same sum value with this test and this test. Thus, we can calculate the frequency because these words having the same value. Okay, so another method of summing up the character value is maybe instead of we assign 1 until 26, we assign them their own value. Maybe we can use their character Unicode integer. Character Unicode integer is the integer that represented by the ASCII code. Okay, so for example, ASCII code table. So another way is we may get its ASCII code table and sum up. Okay, so there are, for example, T. Where is T? T. Here, T. So hexadecimal ASCII code for T is 74, or here is a decimal value is 6116. So that is one of the method lah, because this method is actually coming from yourself, your own logical thinking. Okay, so how do you want to calculate the frequency of words? Okay, so far so good.
Okay.
Kelvin? Okay. So hash code algorithm is based on your logical thinking. So these are some of the suggestions. Okay, so maybe you may have a better way to calculate the frequency of words. Who knows, right? Okay, so we proceed. So because of problem like just now, how to finding the frequency of words. So the expert coming with ADT dictionary. Okay, the expert coming with an object, abstract data type dictionary to cater the problem like the previous problem. Okay, so this ADT dictionary, also known as map, table, or associative array. So this object, this ADT, will have two parts, which is a search key and the value for that key. Okay, so it is like our dictionary lah, our usual dictionary. You will have words, and then there will be a description of that words. So the key is the word, the root words, and then the description is the value. Okay, so just imagine it like that. So it is ADT dictionary. Okay, so this ADT dictionary organizes and identifies entry by their search key. Okay, so whenever there are process of organizing the data inside the dictionary, or identifies any entry inside that dictionary, it will use the search key, the first part. Okay, so it is like a unique ID lah. The search key will become the unique ID to if you want to process, or if you want to organize and identify any entry inside that dictionary. So this ADT dictionary can retrieve or remove an entry from a dictionary given only the entry search key. So if you want to retrieve something, and then if you want to remove that entry from that dictionary, then you can just, it is enough if you know the search key. Okay, so an entry here is referring to the couple, to this couple lah. It has a search key, and then it has the value. So we call it as an entry. So these are few applications that can use the dictionary ADT, which is the first is the directory of telephone number. If we want to develop an application that listing out all of the telephone number in some areas or in Malaysia, then we can use ADT. Just use ADT. Then after that, we also can use it in computing frequency of words, like the first problem that we learned previously. And Lastly, the concordance of words. We can use the dictionary to implement or to develop a concordance of word applications. So concordance is actually a list of words. Okay, so concordance is actually a list of words. So it is alphabetical list of words. So each of the words, it is um, sorted based on alphabetical. Okay, it is sorted alphabetically. Okay, so the example of concordance is, you can see here. So these are the example of concordance of words. Okay, so when if you want to develop something like this, this is what we call as a concordance. Okay, but we won't touch that lah. We will later learn about I mean none of this we will learn only frequency of words we will cover later in our practical. Okay, so so the ADT dictionary use Java class library, which is map. Okay, so this map interface will be implemented by various classes, which is hash map, hash table, and tree map. Okay, so all of this will override the hash code methods from the map interface. Okay, so if you see in chapter 10 sample code, you will see this class, which is it containing two fields, which is first word and then second is count. Okay, so this word act as a search key. Count is the frequency. It is act as the value, but it is containing the frequency, the count of the frequency of that word. Okay, so the hash code inside the word.java is overridden to simply return the sum of Unicode values of all of the character in the word. Okay, so here it is using the Unicode. It is not using the self-assigned 1 until 26 or 1 until 52 just now. You remember just now the algorithm of choosing the integers character value? Okay, so this word so here. So this word having two property, which is the string, meaning the word, it is become the key, and then integer count that is act as the value. So the hash code here is returning the frequency of that word exists in a given text. So the integer count will receive the hash code. Yeah. So the frequency of words is another class that you can see. It is using the map and hash map. Frequency of words. So it is implementing. Oh, here. Okay, so it is implementing the map and hash map. So we will see the implementation of this letter in the frequency of words. How that map and hash map will be used in order to calculate the frequency of words. Okay, so the specification of ADT dictionary, so it has a data. The data is the pairs of object, which is it is containing the key and the value. And then it will also containing the number of pairs in the collection. So there are various operations that you can do in dictionary ADT, which is this. Add, remove, retrieve content, either it is full or you can get the number of the entries inside that dictionary, or you can remove all of the entries by setting the entries equal to null. Okay, so this is the example of class diagram for a telephone directory. Okay, so telephone directory is like just your a dictionary, but it is only containing all of the telephone number inside maybe certain area. Okay, so you may have one class of dictionary, and then this dictionary will be implemented by a class which we called as a telephone directory. So it will implement the dictionary class, and then this will have a property which is phone book, and then it will have a method read file and get phone number. So this directory will have a property, not a property, like two property, which is name and string. Okay, so because searching database is widely used in computer application, so a dictionary is a very important ADT. So it is a type of ADT that is actually usually widely used. Okay, so even more important is the efficiency of the searching process to locate an entry in a dictionary. So this chapter introduce a technique called hashing that ideally can result in big O1 search times, meaning when you do searching in dictionary, it will be very fast because it having efficiency big O of 1. Okay, so remember big O of 1 is the fastest, right? You have learned about that, right? Okay. So the hashing. So the hashing, right? So in this dictionary, it will implement a hash code method, right? And then in that hash code method, it will use a technique called hashing. So what is hashing? Okay, so hashing is a technique that determine an index or location of a storage an item in a data structure without doing searching. Because because the key itself is containing the locations or the index of the data. Okay, so it doesn't need to do searching because the key itself containing the location or index of that data already. So a hash functions map the search key of an entry into a location that will contain the item. Okay, so this hash function will return the hash index of an entry in the hash table. Hash table is the location or a part of data that containing all of your data that you input in your dictionary. Okay, so it is called as a hash table. Okay, so this hash function will return the index or the address of the value that you want to find in the hash table. So an hash table is an array that contains the entries as assigned by the hash function. So you have a dictionary. That dictionary have a lot of entries. So that is what we call as hash table. So the index or a location computed by the hash functions is known as the hash index. Okay, so the index or the location of that entry is known as hash index. After it compute the index of that entry, it is called as hash index. A perfect hash functions map each key, each search key into a different integer suitable as an index to the hash table. So we proceed. Use of hash functions. So this is the example of how you can use a hash function. So in dictionary operation that add or retrieve entries, so both operation will use hash functions because, for example, here you want to um, add new entry to your hash table. So here you will receive a key and a value, and then the index will be computed by the hash functions. Okay, so after that, the index that is computed by the hash operations, the hash functions will become the index of that value when you want to insert it in the hash table. Okay, so after that, if you want to retrieve a value, you just need a key of that value that you want to retrieve. So in order to retrieve, the index will need to it need to be computed by the hash functions first before it can get the real index in from that hash table. Okay, so understand how this hash functions works in add and retrieve method or algorithm. Wait, I need to take this call. Hello? Hello, ya, selamat pagi. Okay, sorry guys. So up until here, can you understand about the hash functions, how it is used in add and retrieve? Kelvin and Noel?
Oh yeah.
Yeah.
Okay, sorry about that call just now. Okay, so there are two steps of hash function. I want to silence my phone first. Okay, so there are two steps of hash functions. There are two steps in the hash functions just now that we use in add and retrieve. So first, it will convert the search key into an integer called the hash code. Okay, so that is the first step. And then after that, it will compress the hash code into the range of indices of the hash table. So because um, the hash table has a limited range. So it needs to compress the hash code so that it can fit to the hash table. So this is the example of algorithm in the hash functions just now. First, for example, you have the phone number already. Maybe your phone number 0, 0, 1, 4, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so after that, you will convert the search key into an integer called hash code. So first, maybe we will only take the code here. For example, only for last 4 digit of phone number. So if you have 1, 2, 3, 1, 2, 3, 4, 5, 6, 7 up until 10 lah konon. Okay, so maybe you only take 10, 9, 8, 7 as the code. Okay, so it will become the hash code. After that, the algorithm will return it will compress the code so that it can fit into the hash table. So in order to compress that hash code, it will need to apply some computation. So here it is using a modular. Okay, so and then the result of this is actually will be shorter. So it will be shorter so that it can map or it can fit the hash table. Okay, so we will see the more example about this later, about this I modular table size. We will learn about that functions after this. Okay, so for a hash functions to be said to a good function is it must minimize collisions. So we will learn about collisions later, meaning this collision is actually one index or there are various entry pointing to one index. So it is what we call as collisions. One index having more than one entries. So we don't want it actually. So if it has no collision or minimum number of collisions, then your hash functions is a good function. Okay, so after that, distribute entries uniformly throughout the hash table. Okay, so for example, you have an array, a linear array, and then when you when there are any new entry to that table or that hash table, the entry will be distributed uniformly, meaning they are in the first, they are in the middle, they are in the end of that hash table. It didn't only group in one place. It not only group at the left or all of the entries are grouped in the right, okay, or all of the entries grouped in the middle of that hash table. So a good hash function should can distribute all of the entry uniformly throughout the hash tables. It is not only macam berat sebelah or only at the end or only at the beginning or in the middle. Okay, so your hash function also must be fast to compute. So this hash functions is referring, remember it is referring to this. So whenever it do these two process, it must be fast. Okay, and then your formula here must can distribute all the entries uniformly. This process actually it can determine the index, right? It can determine the index of that entry in the hash table. So it should can put the entry like I said previously, it must be in uniform. Okay, so the search key used for computing the hash code can either be the primitive type or an instance of a class. So the primitive type is I want to ask, what are the example of primitive type of data? Primitive type, primitive type, primitive type of data lah. Yes, it is the existing class, or it is actually not ADT, but it is the existing inside the Java functions. We have string, it is a data type, right? It is, but ADT is abstract data type. But primitive type is a primitive data type. For example, your string, your integer, your double, character, it is the existing data type that is predetermined in Java. Okay, so your search key can be a primitive type of instance of a class. Okay, so remember just now, in order to compute a hash code, it will need a Java class, which is called as an object. Okay, so in that object class, it has a method that need to be override by any classes that will implement that object class. So the default implementation return an integer value based on the invoking object memory address. So not appropriate for hashing because equal distinct object will have different hash code. Okay, but the default implementation of this hash code is not really appropriate because when there are two objects, which is actually distinct object, it is actually a similar distinct object. Equal is distinct object, meaning it is similar distinct object. It is actually, you can see it is a similar, but this hash code produce different hash codes. But it actually should have the same hash codes because that object has equal distinct object. So it should have a same hash code. But this hash code from object, this class object is not really appropriate because it will return different hash code. So that's why we need to override the hash code method in this object class to map equal object into the same location in a hash table for use in a dictionary implementation. So this is the guideline when we want to defining hash code or when we want to override the hash code from that object class. So this is your guideline. First, if a class override the method equals, it should override hash code. Okay, so if you have a class, you are overriding method equals in the object class, then you also should override the hashcode method. So if the method equals consider two objects is equal, hashcode must return the same value for both of that object. Okay, so the hashcode that is written by the method should return the same value of two objects that is considered equals by the equals method. So if an object invokes hashcode more than once during execution of program on the same data, it must also return the same hashcode. Okay, so another guideline is an object hash an object hashcode during one execution of a program can differ from its hash code during another execution of the same program. Okay, so if you run your program at 9 a.m. and then if you run your program, your hash code program at 9 a.m. this morning. And then after that, at 10 p.m., you are running the same program using the same data, but the second execution will give a different hash code. Okay, so the hash code will be different from one execution to another execution. Okay, so this is the method, the algorithm that you can use if you want to override hash codes, or if you want to develop hash codes methods for string. Okay, so here we are using the Unicode of that string to in the computation. So we are not using 1 until 52 just now lah. So we use the Unicode. Okay, so the method or the algorithm here, first, in your method, it should have this algorithm. Okay, so first you add up each of the character Unicode value. Okay, so each of the ASCII representative of each of these character you need to add up, and then multiply each character Unicode value with the character position within the string, and then sum the product. It will be a better approach. So these are the honor methods. This method is better than the first and second method, and better than the previous method here lah. Okay, so this honors method is using sum. These are the how it will produce the key. Okay, so it use this computation. It is not using modular, but it used this, which is G multiply hash. Hash is the multiplied by hash plus S, and plus the character, the Unicode character value here. Okay, so G is a positive constant. So don't ask me why they come out with this formula, because it is produced by Honor. This Honor is maybe the name of that method creator. Okay, so if you are creating hash codes for string, then maybe it is better if you use this method. which is Horner's method. Okay, so these are the example of add primitive type. So we will actually have a specific way of calculating a primitive data type. I mean, how you operate primitive data type when you use hash code will be different if we the operation of hash code for ADT. Okay, so for the primitive type, when we want to create hash code for the primitive type, we use the primitive type key itself. Okay, so these are the methods. Okay, so we will manipulate the internal binary representation of that of that primitive type, and then we use folding. So what is folding? Folding is the process of we break the key into a group of digits and then combine the group using either addition or bitwise operator, such as the exclusive OR. So there are some process here, which is in the folding, where we will break all of the key, only the key part, into groups of digits, and then we combine again by using addition or bitwise operator. Okay, so the number of digits in a group should correspond to the size of the array. So the number of the digit in the group, it should be correspond with the size of the array. It cannot be over or smaller than the size of the array lah. Okay, so compressing a hash code. This is the second step in the hash code method. Remember, you need to compress it so that it can fit into the index range of the hash table. So we must compress the hash code so it fits into the index range of that hash table. Okay, so the method to compress the hash code is by using this C modular n. Okay, so n is the prime number, so it is the size of the table. Let's say your array is 11. So n is the size of your array lah. Okay, so how big or how much component inside your array. Okay, so prime number is a number that can divide by 1 and by itself. Okay, so when it divide by 1 and when it divide by itself, it doesn't produce any balance. Okay, so that is the prime number. So the prime number is, for example, 2, 3, 11, 9. When you divide it by 1 or by itself, I mean, it only can divide by 1 and by itself. If it divide by other number, then it will produce a balance. Okay, so that is the prime number. But the size of the hash table must be in prime number lah, in order for you to do the compressing of the hash code. Okay, so if hash index is negative, add the size of the table. So index will then be between 0 and n minus 1. Okay, so this n is the size of your table lah. Okay, so because you start with 0, that's why at the end of your table, it must be n minus 1. So this is how this method is represented in code. So if you have these functions and then it only needs the key. So after that, if you remember in the hash code method, the first step is to get the index, and then after that we compress it. So this is how you compress it. Okay, so hash index is the hash code, this key, this key value actually, key.hash code. This method is actually returning the key, the value of this key. Okay, so the value of that key modular with the length of your table or the size of your table. Okay, so if your hash index returning smaller than 0, meaning there are no in yeah, if your hash index returning smaller than 0, then you will need to return, meaning here lah, if the hash index is negative at the size of the table. So if your hash index is negative, so you need to return the hash table length. Okay, so this hash index is negative, right? So you need to negative here plus the hash table length. So this is the operations of how to compress the hash code. Okay, so if you want to see the implementation of dictionary using the hashing technique, you can find it in this folder in our chapter 10, hashing dictionary interface.java. So it will have method add, remove, get value, content is empty, is full, get size, and clear. Okay. So okay, so this is the case study that implement the telephone number just now. Okay, so in Higley town, everyone telephone number begins with 555, and then after that it is followed by a unique number lah. Okay, so they require an emergency information system which enable them to retrieve the street address associated with each telephone number. So we will use the hash function that will convert the telephone number into its last 4 digits. So this is continuously from the example that we see previously. If you both remember, we use the last 4 digit of that phone number to create the hash code and to compress it lah. Meaning in order to create the hash code. But in order to try the implementation of the hash function like hash code. So in the hash table, we would place a reference to the street address associated with this telephone number in hash table, which is 1214. So for example, you have this phone number. This phone number is coming from someone that is living in Higley town. So that person has a unique the last 4 number lah in his phone number. And then if the cost of evaluating the hash functions is low, adding an entry to the array hash table is an big O of 1 operations. Cost of evaluating the hash function is low. Adding an entry to the array hash table is okay, wait. here, I will show later a video about evaluating the cost, evaluating the load factor actually in here. But if that cost of evaluating, or what we call as a load factor, is low, but later we will show, we will watch a video about this, is low. When it is low, then adding an entry to the array hash table is big O of n operations, meaning it will be faster. Okay, so cost of evaluating is actually number of items that is stored divided by the size of array. The lower the load factor or cost of the evaluating, the faster the adding operation to that hash table. The faster the operation of adding to that hash table. Okay, so for example, I will show the how the cost of evaluating lah later. But for now, it is enough for you both to know that if the cost of evaluating or the load factor is low, then meaning there are a lot of place in that hash table that can be entered by new entry. So if that load of factor is low, meaning there are a lot of place, or there are a lot of place lah to be, and we can enter new entry in that hash table. So that is what it means by here. That's why the operations can be a big O of one notation, because you have a lot of rooms, empty room. If you want to enter new entry, then if there are a lot of rooms to be entered, then the insertion will be faster. Okay? Okay, so this is the example. If you have one number here, a handphone number, so we are now, so here is 1214 is the street address for this phone number, and then it will be stored in the hash table. So imagine you have this hash table. So a hash function index its hash table. So hash functions will create an index for small room here. Okay, so this is the value of that room, but in order to come out with the index or the address of this room, you need to undergo this process, which is the process of hashing. Okay, so the process of hashing, so remember first, getting the index, and then second, compress the index. It is the process of hashing. So first, this is when you want to add new entry in your hash table. Let's say you want to enter this entry. So first, we will need to get, or we need to do the hashing in order to get the index. This index is the address of this room. And then after that, baru we can enter the value after we get the index. Because this index is already containing, it is containing the compressed value of your hash code, which is actually when we do searching letter, we just need to the key of that entry, and then we already know the location, because in the key itself, it is containing the address already. So that's why, so this is the process of adding. Okay, so before we add, we need to compute its hash index first. Okay. So far so good, Kelvin and Noel.
Okay.
Okay.
Okay. So just now we are learning about the adding. So now we are learning about retrieving. How we can retrieve the an entry from hash table. So to retrieve the street address associated with the number, this number, we once again compute the hash code for this number and use the result to index the hash table. Thus, from hash table this index, we get the desired street street address. So yeah, so here, in order to get the value, we just need the key. So the key will need to go undergo the process of hash code or indexing first, and then you can get the value of that hash table given the index. And so this operation is also big O of 1, meaning it is fast. Notice that we did not search the array of hash table. So we don't need to do like the previous linear search. You need to check one by one the value of that index. If you want to search something, we need to search one by one, right? We do the looping to start to find the array or the value inside the array. But using dictionary, or using the method of hash code or hashing technique, we don't need to do any searching, because in that key, it is already containing the index. So as long as you know the key, and then we can directly, the system can directly go to the index, because the key is already having the index. Okay, so will this algorithm always work? So we can make them work if we know all of the possible search key. So this algorithm will always work if you know all of the possible search key, meaning you at least you know the range. If you don't know the range, meaning this algorithm cannot be work. Okay, so there must be a problem if we don't know the range or the possible of the search key. So in this case study, the search keys range from 555,000 up until 555,999, because we know that this is the range of the phone number in that town, the Higley town, if I'm not mistaken previously, the Higley town. So the hash functions will produce indices from 0 to 999. So we know this range. So algorithm of that hash code, what we have learned previously, will work in this case study because we know the range. If the array hash table has 10,000 elements, each telephone number will correspond to one unique element in hash table. So that element represents the appropriate street address. So from 1 to 999, there will be a 10 elements because it is start from 0. Kan? So that's why actually the size of the element is 10,000 if the range from 0 to 9999. So this scenario describes the ideal case for hashing. And the hash function here is the perfect hash function. So if you know the range of the key, meaning if you know the from start until the end of your hash table, then you can have a perfect hash function here. What is the perfect hash functions? Remember just now there are three criteria, which is first, it must minimize the collision. Second, all of the data must be distributed uniformly. And then the third is the computation must be fast. So if you know the range, you can meet that perfect hashing. Okay, so if you know the range, you can meet the perfect hashing. You can have a perfect method of hashing if you know the data, if you know the range of your data. So hash table size. In the Higley town, we only required only 700 telephone number. Excuse me. In the Higley town, only required 700 telephone number, meaning that town is very small. Only 700 people use that. Only 700 people has a phone number lah. Meaning maybe if it is more than maybe if that town has more than 700 residents, then maybe they don't use phone lah. But only 700 residents in Higley town have a phone, and then only 700 telephone number lah. So most of the 10,000 location hash table will be unused. So we will waste most of the space allocated to the hash table. So out of the 10,000 of the location in your hash table, only 700 will be occupied. So another 9,300 location will be a waste. Okay, so if the 700 number were not sequential, we would need a different hash function if we wanted to use a smaller hash table. Okay, so if all of that number were not arranged sequentially in that hash table, so we will need different hash function, meaning we need different hash formula. Maybe we don't need to use the hash modular or n modular, hash modular, key modular n previously. If we want to use the smaller hash table. So the two-step of hash functions, if you want to use a smaller hash table, is convert each key into an integer called hash code. This is what step inside the hash code previously. So remember, first we need to get the hash code, and then we need to identify the hash code. So if previously, if the number, phone number is 555 and then 123, so the hash code that we identified is 123 lah, the last four. So that is become our hash code. So after that, you compress the hash code. You compress the 1214 last time, and then you compress that 1214 using that modular formula. That is how you compress the hash code. Okay, so these are the two steps of hash function. So this is more clear example of the hash functions just now, following the case study in the Higley town. Okay, so the hash function convert a telephone number into its last four digits. For example, if you have this phone number, the hash code that you get here is 1264. Meaning each of the telephone number, the 700 telephone number we only will get its last four digits to become the hash code, which is the step one in your hash code. So after that, you compress the hash code just now. Okay, so let's say the hash table is the hash table size is 101. So um, so how do you get the index? Meaning how you will arrange your telephone number in the 101 size of hash table is by using this. You didn't put the hash table, hash code just now, like 1 until 700 lah. Okay, but instead we are getting the index by computing the index by using the modular formula. Sorry. So why we didn't put that 700 of telephone number sequentially? Because it will make your hash table like berat sebelah. Up until 0 until 699 index in your hash table will be occupied. Meaning the distribution of your data will not uniform because it is only berat sebelah. So that's why we need to use the indexing. The indexing will calculate the index of each of the entry or each of the phone number into, and it will distribute it evenly in 101 hash table. So the example of hash code is, or the index, the process of compressing of that hash code is this one. Hash code modulo 101. Okay, so 101 is the n, meaning the length or the size of your table, hash table. So let's say we get the hash code is here 1264, and then you modular it, hash code is here lah, 1264 modular 101, then you will get 52. Who are not clear here how we can get 52? How to do these operations? Who don't know how the modular operations are happening or computed? In short, who here don't know how to compute the modular? Yeah, 52 is the remainder. Kelvin, know ka? Do you know how we can come out with 52? Okay lah. So I don't need to explain here lah. The modular is you get the remainder. Okay, so you get the remainder, and then this index will become the index of 1264. So imagine you have a hash table that has 101 location, and then this 1264 phone number will be key into the location 52 in your hash table. Okay, so these are the, recall again the algorithm in the hash functions, where your first is get the hash code, and then second is to calculate or compress your hash code. So in order to compress your hash code, you will need some formula, which is in here. In this case, we are using modular. Okay, collision. So these are the problem we will meet if we are using a dictionary. Because when you adding some entry, if you are adding entry in a dictionary or in your hash table, there might be a possibility that one index can contain more than one value. Okay, so that is what we called as collisions. But before we go further into this, we take 5 minutes break. So we meet again at 10:21. Okay? Okay. Okay, so in before we go to the collisions, I want you both watch this video lah to understand the collisions more. sorry ya.
Needless to say,
Can you
that is
both
unrealistic.
hear the voice?
Sometimes, if you apply a hash function to two different
Yeah.
it generates the same
Is it
index
clear?
number for both. But both items can't go in the same place. This is known as a collision.
Okay, so
Needless to
change
say,
here.
that was
So
unrealistic.
I will make it.
Sometimes, if you apply a hash function to two different keys, it generates the same index number for both. Sometimes, if you apply a hash function to two different keys, it generates the same index number for both. But both items can't.
Oh,
This is known as a collision. Both items can't go in the same place. Function to two different keys, it generates the same index number for both. But both items can't go in the same place. This is known as a collision. Let's load up the array again, but this time with a different set of data. Mia goes in at position 4. Tim goes in at position 1, just as before. B goes in at position 0. When we do the calculation for Zoe, she goes in at position 5. But then along comes Sue. And when we calculate an index for Sue, we get position 4. But this is already occupied. So we look at the next place along. But this too is occupied. But the next place along isn't. So that is where we're going to place Sue. The calculated position for Len is 1. But this too is occupied. So Len has to go into the next available space. Mo wants position 3. No problem here. Lou wants to go into position 7. Again, no problem here. But Ray wants position 5, and position 5 is occupied. So is position 6 and 7. So Ray has to go in at position 8. Max wants position 8, but of course this is occupied. So Max goes in at position 9. And finally, Todd wants position 9, but he's going to have to settle for position 10. Resolving a collision by placing an item somewhere other than its calculated address is called open addressing, because every location is open to any item. Open addressing can use a variety of techniques to decide where to place an item that doesn't go where it should. This particular open addressing technique is called linear probing. If the calculated address is occupied, then a linear search is used to find the next available slot. If linear probing gets to the end of the array and it still can't find a free space, it might cycle around to the beginning of the array and continue searching from there. To look up an item in this hash table, the hashing function is applied again. But if there have been collisions and some items are not in their calculated positions, then finding an item will also involve linear probing, that is, a linear search.
okay. So in this video, it shows you it shows you one of the type of collisions resolutions. Okay, so which is the linear probing. Okay, so we will cover that we will go back to our slide. Okay, so the linear probing, it is like if you cannot find the index after we calculate its hash code, and then we cannot find the index because it is already occupied, then you will need to find the next available place or index. So that is the linear. It is actually under category of open addressing. but under category, there are actually various way of open addressing, way of finding an index, a replacement index. But the one that is showed just now is linear probing. So we will learn another two later. Okay, so hash functions gives two different entry the same hash index. Okay, so sorry. So what if the hash functions, all of that we calculated just now, it gives two different entries but using the same hash index. Okay, so they are referencing to the same room, but actually they are more than one person. Okay, so when you go through the process of hash code for this number, phone number, both will end up to the position 52 or index 52 in hash table. So if we have already stored the street address for the first number here in 52 location, so what we will do to the next address or the next phone number here? Okay, so because both of them are referring to the same index. So handling this type of problem we called as a collision resolution. So collision resolution caused by hash functions is represented by this diagram. So both this number after we do the hash code, then both referring to the same address. Okay, so that is what is happening. So when we are using the typical hash functions, it is not perfect because they can allow more than one search key to map into a single index. Okay, so the previous hash functions is not perfect because they give two person the same index room, okay, same locations. So this is what we call as the collisions lah. The collisions occur when the hash functions maps more than one item into the same array locations. Okay, so you can see here the example of these collisions in the hash dictionary driver.java. Okay, so when the last four entries are added, so you can run this driver letter, this Java, this class or this applications later to see how the collisions is resolved using the collision resolutions. So what to do if the hash function's return location that is already in use in the hash table? So first, we need to use another location in the table. So the second step is we need to change the structure of hash table so that each array location can represent multiple values. Meaning to say that one locations can accept multiple value. So you need to change the structure of your hash table. So there are, like I said just now, in the video, it is showing the open addressing approach, which is the first, the one that it shows just now is linear probing, where it will find the next available index or room in that hash table if the index is already occupied. So we will learn about this tree after this. I mean in the next slide. So linear probing, both of you already can see it from our video just now. Okay, so but this is the explanations about the linear probing lah. So open addressing scheme locates alternate location within the hash table. Okay, so we called it as a open addressing because they are meaning any available room or location inside that hash table, as long as it is still available, it is open for any item or any entry to be keyed into it. Okay, so that is what we call as open addressing. Okay, so open addressing have three specific way of how to uh, replace the index that already occupied. Okay, so first is a linear probing. So if the collision occur at the index that is computed, then it will find the next available room or index, next available location in that hash table. Okay, so that is a linear probing. So search the hash table sequentially. So it will search the hash table sequentially after one, and then two, and then three, and then four. So it will following the number lah sequentially. So it will find for a vacant cell, and then it will increment until the empty cell will be is found. So when it is searched until the end of the table, it will continue at the beginning of the table. Okay, so this is the example of linear probing. Um, um, for example, here, after you enter four entries in this hash table, so there are a problem which is during the retrieval we cannot tell because you put it all inside this 52, and then during the retrieval we cannot tell which address is the right for the given phone number. So the solution for this problem is we package all of this search key. We package a search key with its value, meaning you package it under 150 Main Street because all of this phone number is from this address or from this location. So another example of linear probing is a revisions of the hash table shown in 18.3, which is here. 18.3, wait, 18.3. This is 18.2. Actually, this is 18.3, not figure 21. This is 18.3. So a revision of the hash table shown in 18.3. So 18.3 is this one, not 21.3. Okay, so this I will screenshot lah. Okay, so a revision of a hash table that is shown in 18.3, which is here, when linear probing resolve collisions. So each entry contain a search key and its associated value. Okay, so wait, so here, if you this is the previous one when there are four phone number referencing to the same index. So now it says that in the previous, the solution is we package a search key with its value. We package all of the search key with the value here. Meaning we package all of these by using the name of this, the value, based on its value. Because all of these having the same value. Okay, so after that, so now I cannot see actually the difference between this diagram. Yeah, there are no difference between this diagram. Right? Can you both spot which are the difference between these two diagram? There are no difference, right?
Yeah, no difference.
Yeah, that's why I don't know how what is the difference here. Okay, so but what it want to tell here is actually when we have this problem, when there are more than one entries that have the same index, then the solutions here, it says that we package all of the search key. So search key here is all of the value of the hash code, and then we package it with its value. So just it says that here is the revision. So just revision lah. Okay, so um, if you see here, each of these will be given its own room lah. Okay, so because all of here it is all pointing to 52, so only the 1214 will be entered in here. But the next, which is at 132, will be go to the next empty space lah, which is 53. So here the this one will go to the 53, this one will go to 54, this one will go to 55. So like what we watch in the video just now, whenever they are occupied index, then even though the entry has the same index, it will go to the next available room. Okay, so if you want to remove an entry using the linear probing, so we can just use a method remove, and then that method remove will just assign the entry or the entry with null. Okay, so that is how the process of removing, or the process of removing the an entry in hash table, which is assign null lah to that entry key. Okay, so in your hash table, there will be three types of locations. Okay, in each of the hash table, it has its own room, and then there are three status of each of that room. So first, it is occupied. Okay, so where the location reference and entry in the dictionary, meaning the index already have um, a value lah. And then after that, empty will have null value. Okay, so it has null, meaning the locations, the index is null. So available is the location entry was removed from the dictionary. Okay, so um, the one that will be occupied is a location with available status. So empty, which is null, will not be, meaning if you have an operation to enter entry to your hash table, you will find a location with available status, not an empty status. Okay, so we will see later why. Okay, so only a location with available status will be occupied or will be occupied by new entry. So for open addressing, why do we remove an entry by placing it in an available state instead of setting it table location to null? So when you do the remove in the remove method, we will um, change the status of the location into available, not an empty. Okay, so during the remove, if you see previously here, um, if you remove an entry here, it will take it will actually apply. Meaning it will you will the entry value will be replacing by null, but the status will be available, not empty. Okay, so it will, even though it is null, even though the remove method make it null in the previous here, but the status of that location will be available, not empty. So why do remove an entry by placing it an available state instead of setting it location to null? So it is to avoid premature termination of probe during retrieval or future removals. Okay, so actually during the process of the process of probing is the process of searching an empty available, no, sorry, the process of probing is the process of searching available locations. Okay, not an empty locations, available locations. So that's why when you remove an entry, the state will become available, not empty, because if you put it as an empty, the process of probing will stop there. Okay, so we will see it in the next example. So to retrieve an entry, um, okay, so this is the operation in the dictionary entity that will require some searching. For example, to retrieve an entry, to remove an entry, or to add an entry. So you need to do some searching when you do these operations. So first, for the retrieve an entry, you need to search the probe sequence for the key. So during the retrieve entry, you will the process will examine the entries that are present. Then it will ignore the location if it is in the available step. Okay, so it will stop search when the key is found or null reach. So that's why here it is what it means by to avoid premature termination of probe during retrieval or future removals. Because if the process of probe found null location, it will stop the process. It will stop the process. So that's why we cannot, when we do the operations of remove, we cannot make the state of that location into empty. Instead, we need to make the state of that location to available when you do the remove method. Okay, so after that, another operations that requires searching is to remove. So when remove operations happen, search the probe sequence same as for retrieval. So first you will need to search for the key lah, the key that you want to remove. Okay, so if the key is found, mark location as available. Okay, so you mark the location as available, not empty. Because why? If there are any retrieval letter, the process of retrieval, it will stop early if you mark the location as null. Okay, so because this is makes the process of probing will stop when empty or null locations is reached. So to add an entry, you will need to search probe sequence same as for retrieval. Okay, so after that, not first available slot, and then if you found first available slot, then um, use that available slot. Okay, so that is what happening in linear probing. So here, let's say we have this hash table and there are few locations in it. So this A is the process after you add an entry. So you maybe you add an entry here. So before that, the blue here is the current entry, the one that is just entered. The light gray, which is here, is the remove entries, meaning the available locations. The dark gray is the location which is null. Okay, so um, a diagram here, it is displaying when there are new entry added to that hash table. So we can see here there are 4 new entry added. Okay, so after that B, it is the process after you remove the location 53 and 54. So that's why it is become light gray. So C, after a search, okay, so when a searching happening, it will stop the searching in the null. Here is actually um, the dark gray actually. Location 56 is actually dark gray. But here it is looks like light gray already. So this is actually not empty, but it is actually dark gray, which is null. Okay, so when the searching happening in this hash code or the probing process happening, then the searching will ends at 55 because 56 is actually null. Okay, so after that, D during the search while adding an entry. So here, when you want to add new entry, first it will search the first location here. So it is 52 because it is occupied. Then the process ends, and even the process of searching available slot will be continue. It will continue up until it found a null locations here. So after that, after it search up until here, then it will put the new entry in here. It will place the entry in the first available location that it found, which is in 53. So in E, it is displaying after an addition to a formerly occupied locations. Okay, so here is the 53 is most addition that can be found faster in location 53 than if it were placed into location 54 or 56. So it will add the new addition, like I said, to the first available location that it found. Okay, so it will not place it in 54 because when it put it in 53, this if they are searching later, this location can be found faster than 54. So these are the implementation example of code of the linear probing. So you both can refer to this example in our sample code chapter 10. Okay, so this class having these methods, which is probe, locate, is the hash table to full or the next prime, get the next prime or is prime. So after that, this is the driver. This is to test the code inside the hash dictionary.java, and then the student Java, and then the name of the Java. So all of this student name and driver.java is implementing the hash dictionary.java. So what are the advantage of linear probing compared to the another two method under open addressing? Okay, so the advantage of linear probing is it can reach every location in the hash table. Okay, so meaning because when it is searching for available slot or room in the hash table, it will check each of the room, so or slot. That's why it says that it is the advantage because it can reach each location in the hash table. So this property is important since it guarantees the success of the add operation when the hash table is not full. Okay, so um, yeah, so this is important lah to the add operations because by this advantage, it can make sure that the add operations can be done if that hash table is not full. But the disadvantage of linear probing is primary clustering. When you do this method, it can cause a primary clustering. So what is the primary clustering? It is a cluster, uh, it is a group of consecutive table location that are occupied. Okay, so meaning to say that, like here, imagine you have a long hash table, but if you are using linear probing, it will occupy a group of location in the hash table. Your hash table will not be uniformly occupied. it only will occupy some part of your hash table. So that is what we call as primary clustering. Okay, so another definition of primary clustering is um, it is the key that it found using this linear probing will be bunched together in an array, while large proportion of it are remain occupied. So, like I said just now, lah, only some or certain part of that hash table will be occupied, but the others will be unoccupied. So it is not even. So this primary cluster can combine it to form larger cluster. Okay, so it can become larger cluster. So this leads to long probe sequence and hence deteriorations in hash table efficiency. Okay, so if the primary cluster become bigger and bigger, so the when you do the linear probing, it will take a longer time. So your searching efficiency also become deteriorate. Okay, so another method under open addressing, meaning open addressing is how you find available slot when the index is already occupied. So which is another way beside the linear probing just now is by quadratic probing. And then after that, double hashing. So we will cover that in our next lecture lah. Okay, so up until now we only cover up until linear probing. Okay, so um, is the linear probing clear, Noel and Kelvin?
Yeah.
Okay, so just imagine the video that we watched previously lah. Okay, so when the index is already occupied, then it will search another available locations, and then the status of each of the location inside your hash table there will be three, which is occupied, empty, and available. So only available status that can be occupied. The empty one will be used um, as the will be used either the searching will stop or not, because that is the responsibility of the null location. Okay, so remember the null location will not be used to enter new entry, because the searching will stop at the null status locations. Okay, so after that, we have learned about the disadvantage and advantage of linear probing, and then yeah, so next week we will learn another two open addressing, which is the quadratic and double hashings. Oh, got some I confused a bit. We are in 11:01 a.m. So can you please just jot down what you confused, and then we will discuss that on next week. Okay? Noel? Yeah. Okay, so since we already 11:01 a.m., then we can dismiss our class. Okay, bye.
Okay. Thank you, miss.